I'm Kelly. Now I will present the introduction and the differences between microcontroller and microprocessor. This project provides a comprehensive exploration into fundamental differences between microprocessor and microcontroller, as well as their respective architectures and use cases. It begins by discussing the core distinction in how these two types of processing unit functions, emphasizing how MPU are used for general-purpose computing, while MCU are tailored for specific control tasks in embedded systems. The assignment also delves into how high-level programming languages are translated into machine code using tools such as compiler, assembler, and interpreter. Additionally, we compare the language abstraction level across different generations of programming language. To apply this concept particularly, we implemented a sorting algorithm using Python built-in Slingshot and ARM64 assembly instruction sort, allowing us to analyze performance trade-off between high-level and low-level programming. The final outputs include a video presentation summarizing the key findings and particularly insight, bridging theory with real-world application. Now let us move to the differences between microprocessor and microcontroller. Microprocessor and microcontroller differ significantly in architectures, integration, and application. A MPU is a central processing unit designed for general-purpose data processing, often require external components like RAM, ROM, and input-output interface. It is more complex, offers higher processing power, and is typically used in applications demanding flexible and high-performance computing, such as personal computer, server, and AI systems. Conversely, an MCU is an integrated circuit built for specific control tasks, combining the CPU, memory, and peripheral onto a single chip. The high level of integration makes MCU ideal for embedded systems and real-time control in energy-efficient, battery-powered environment. While MPU operate a higher clock speed and support larger external memory, they consume more power and incur high costs due to the need of external components. MCU with their lower clock speed, limited internal memory, and fixed instruction set are optimized for predictable, low-latency behavior. For market-wise, MPU are produced by major players like Intel, AMD, and Qualcomm, while MCU are dominated by manufacturers such as Microchip, Renesas, and Atmel. Ultimately, the choice between MPU and MCU depends on their complexity, performance need, and resource constraint of the application. Furthermore, the real-world commercial example for MPU, like Intel Core i7 12700K and Apple M1 Pro chip, are widely used in laptop and desktop for tasks such as video editing, gaming, and data analysis due to their high performance and multitasking capabilities. On the other hand, real commercial examples for MCU such as STM32 series, ESP32, and ATmega 328P used in Arduino Uno are embedded in devices like smart thermostat, wearable fitness tracker, and industrial sensor, where low power consumption and integrated control functions are essential.
Hello, my name is Priscilla and I will be explaining about part 2 of the assignment, which is the compilers, assemblers, and interpreters. First of all, let us look into the transformation of scripts to machine code for the computer to execute. So there are two phases that we will be talking about, which is the compiled language transformation and the interpreted language transformation. But actually, there's also the assembler that is already included in the compiled language. Basically, it's the same thing, it's just inside the compiled language transformation. So in the compiled language, such as C and C++, the entire program is translated before execution into a binary executable file. The process starts with the source code written in a .c file, in a text file, or also in a text file. Then it will undergo the compiler, which converts this code into assembly language. Afterwards, the assembler will convert the assembly language into an object file, which is the machine code. And finally, a linker will combine all the object files into an executable file, which the CPU can load and run directly. Next, at the interpreted language transformation, there are also a few phases, but there's a difference because the source code is not compiled ahead of time. And for the example I use is Python. So this interpreter reads and executes the code line by line, and it translates each statement into machine code and immediately executes it. But you can see there's like a loop here from the machine code execute and source code. So it'll keep fetching the line until an error occurs. Then the interpreter will stop and show the error, and until the error is fixed, then it will continue the run again. Next, we will move on to the evolution of the programming languages. We have 5 generations of languages. So let us look into the first one, which is the first generation language, and is also known as the machine language, which is the most fundamental form of the programming languages. So this language consists purely of binary code, which is basically ones and zeros, and because of that, it is actually the most closely related to the computer hardware. So there is no need to directly execute. There is no need for further translation, and it can be directly executed. This method also means that there will be a fastest execution and precise hardware control since there is no translation step. However, building programs this way is extremely difficult and error-prone, as programmers must manage every binary detail and memory location manually, which makes it hard to read, debug, or even modify. Also, these programs only run on specific hardware, which lacks portability. Similarly, in the second generation language, it has some improvement, as it introduced symbolic mnemonics that is more human readable, but is still closely related to the machine code. So this, but it has an extra step, which is using the assembler to convert into machine code. It is more simple than the first generation language, but it still requires deep hardware knowledge and remains machine dependent. So managing hardware details like registers and memory is still necessary. Next, we'll move on to the third generation language. In this part, we finally have a higher level language like C, like Java, and basically C++. But C is still a low level language, but both of them still, they need to undergo more translation process, which is the compiler and interpreter, to turn into machine code and be executed. So we as programmers, we build programs by describing logical steps or procedures rather than dealing with the hardware specifics now for the third generation language. And for C, the program is built procedurally, which requires manual memory management and hardware resource control. And the source code is compiled into machine code specific to the target hardware. But in Java, programs are built using object-oriented programming concepts like classes and objects. Java code compiles into platform-independent bytecode executed by the Java Virtual Machine, which enhances portability. These languages increase productivity and code readability, allowing programmers to focus more on solving problems than managing hardware details. However, they sacrifice some control and may have slower execution compared to lower-level languages. For the fourth-generation languages, they are designed for rapid application development, often targeting specific domains like databases or numerical computing. The example languages include SQL, Python, PHP, and MATLAB. The programs in the fourth generation languages are built using declarative or domain-specific commands that perform complex tasks with fewer lines of code, such as a single SQL query can retrieve data from a database without explicitly programming how to access storage. This generation focuses on simplicity and speed for developers, often allowing non-programmers to build applications. However, fourth generation languages trade hardware control and performance for ease of use and rapid development. Lastly is the fifth generation language, which focuses more on artificial intelligence and declarative programming, where programmers specify what the problem is rather than how to solve it. The example languages are Mercury and Prolog, and the programs are built built by defining facts, rules, and constraints. So the language has an inference engine or logic solver which automatically determines the steps to achieve the goal. This automation reduces programming complexity and accelerates AI development. However, the fifth generation language programs require significant computing resources and offer limited control over hardware or low-level operations. They are also mostly used for AI and expert systems rather than general software development. So in summary, the first and second generation language requires programmers to manage hardware details explicitly and write code very close to machine instructions, while the third generation language has developed to introduce human readable syntax and procedural or object-oriented paradigms, object-oriented code to abstract hardware complexity. Next, the fourth generation language has been developed to emphasize ease of use and rapid development, often through domain-specific languages and declarative commands. Lastly, which is the newest the latest generation language, the fifth one. It focuses on problem solving through logic and AI, and letting the system infer how to reach goals automatically. Therefore, in conclusion, as programming languages evolved, the way programs are built shifted from manual, detailed binary coding to abstract high-level specifications that improve productivity, portability, and accessibility.
Hi everyone, I'm Jolene. I will be explaining an ARM64 assembly program that performs insertion sort on an array of integers. Let's start with the data section. We begin with the first line of code, which tells the assembler that we are defining data variables. Next, we have this line of code. This creates an array of 14 integers, which we will be sorting. Then, we define this line of code, which stores the total number of elements in the array. The following line defines string contents. This is used to label the original array output. This will label the output after sorting. We also define this line of code as a format string to print each integer with a space, and finally, this line to add a line break after printing the whole array. Now, we will move on to the code section, marked by section text. We declare this global main, making our main function visible to the linker, and this extend printf, since we will be using the printf function from the library. Inside the main function, we first store the current frame pointer and link register on the stack with this line of code to preserve the return state. Next, we load the address of the array into register S19. This is done using ADRP and ADD to calculate the full 64-bit address. Then, we load the array len into W20 using LDR W20 array len, which is this line of code. Now, we print the original array. We load the address of original message into S0 and call printf, which is the following code. To actually print the array elements, we set W24 to 0 and then call a helper function printArray. This function prints each element of the array using a loop, which we will get to later. Now comes the insertion sort algorithm. We begin by setting the outer loop index I to 1 using this line of code, since in insertion sort, we start from the second element. The label outer loop begins our outer loop. We compare I with the array len. If I is greater than or equal, we jump to short done. Inside the loop, we load the current key element into W22. This is the element we are trying to insert into the shorter part of the array. We set j to I-1 and start the inner loop. If j is less than 0, we have reached the start of the array, so we go to insert key. Otherwise, we load the element at index j and compare it with the key. If the current element is smaller or equal to the key, we go to insert key. If not, we shift the current element one position to the right using str. Then we increment j and continue the inner loop. Once the correct position is found, we insert the key element into its space with strw22. After that, we increment I and continue the outer loop. When sorting is complete, we print the message sorted array and call printArray again to display the sorted values. We end the main function by returning 0 using this line of code. Restoring the frame pointer and link register and returning. Now look at the printArray function. We start by saving the frame pointer and link register again. Then we initialize a loop index I to 0. In the loop, we check if I is less than the array len. If not, we jump to print done. Inside the loop, we load the format string and the current element and call printf to print it. We increment I and continue until all elements are printed. After the loop, we print a new line, restore the previous function state, and return. Once sorting is done, we print out the sorted array message and call the same print function again to show the updated array. As you can see, the numbers are correctly sorted in ascending order, which confirms that the code is working as expected. This shows how insertion sort can be implemented effectively even at a low level using ARM64 assembly.
Hi, my name is Lim Jim. In this session, I'll be presenting the Python versions of the TeamSort program through a short demo. I will also reflect on the development experience using Python and discuss the performance and efficiency differences between Python and assembly. First, let me explain the Python code. It will demonstrate the use of the built-in sort method to arrange a list of integers in ascending order. The program begins by defining a list that contains a series of unsorted integers. It will then print the original array using the print functions, and the key operation is a.sort, which will sort the list in place, meaning it modifies the original list directly without creating a new one. After sorting, the program prints the newly ordered list. This code showcases how simple and concise Python can be when performing common tasks like sorting. Now I am presenting how to run the code. It can run the code by just clicking the run button beside. Then it will print out the original array and sort the list using sort in ascending order. Now reflecting in the development process, developing the Python versions of the sorting program was very straightforward because of Python's high-level features. Instead of writing complex sorting logic, we simply use the built-in sort method, which is already optimized and easy to use. This made the process quick, intuitive, and completely error-free. We didn't have to worry about low-level memory or address management like in assembly. Overall, the code was much more readable and beginner-friendly. While Python may not be as hard as assembly, its simplicity and ease of development made it better choice for this task. Next, come to disparity of performance and efficiency between Python and assembly sections. The performance gap between Python and assembly comes from the fundamental differences as high-level versus low-level language. Python is designed for readability and ease of use, extracting hardware details and offering features like automatic memory management, which speed up development and improve portability. However, these abstractions add overhead because Python is interpreted at runtime, slowing executions. On the other hand, assembly works directly with hardware such as CPU, register, and memory to allow highly optimized, efficient code ideal for performance-critical tasks. But assembly requires deep hardware knowledge, which is complex and isn't portable across different processors. While assembly can be faster, modern compilers for higher-level language have become so advanced that they can produce efficient machine code close to assembly speed. Moreover, algorithm choice often affect performance more than language, as Python efficient sorting algorithm can outperform poorly optimized assembly code. In summary, the trade-off is between Python ease and flexibility versus assembly speed and control, with the best choice depending on the project needs. That's all from me. Thank you.